One of the biggest challenges we have in modeling biological systems, probably the biggest challenge, is modeling the brain. The brain is the most complex kind of matter we know, probably one of the most complex kind of matter that exists in the universe. And it involves multiple scales and a huge complexity, right? It's an estimate that we have around 86 billion neurons in the brain. The brain exhibits dynamical patterns in all potential scales. I just make a kind of a summary of things. On the largest scale, we know from the well-established field of electroencephalography that by measuring small potential changes in the potential, electric potential on the surface of the scalp, we can actually monitor the changes in time of the activity of millions of neurons that are just there. And from there, we can actually find out that the brain, and we'll go to that question in a future lecture, seems to exhibit a mixture of dynamical states involving things that look like random, plus fluctuations, as it happens in epileptic seizures, that involve a huge, almost periodic synchronization of its activity. If we move below that, and there are several ways in doing that, we can actually look at this as a coarse-grained set of areas, each area having a large number of neurons. And that's, again, something that connects with this picture of the electroencephalogram. We take from different areas of the skull, we take data, and this data actually collapse information about a mesoscopic scale of the brain. So you could think in areas, right, that are more or less connected through more long-distance connections, right? But of course, each of these areas is actually made of millions, thousands, depends on the small scale, of neurons, right? And neurons are, for us, the basic unit, and today we'll discuss about how to make a model, a mathematical model of a neuron. And neurons connect to each other, right? As it was shown by Santiago Ramón y Cajal, they are units, they are discrete, and connect to each other thanks to connections whose complexity was unraveled later on, where essentially you see that there's not a continuum as it happens with cells. You send a signal, and there's then a location, right? The synaptic connection, where the neuron that sends a signal, it's called the presynaptic part of the system, the presynaptic neuron, sends a signal. You have a cleft here where transmission of chemicals happens, and that is detected in some receptors, right? And that can either help triggering an excitation to the next neuron, so the neuron might fire, or on the opposite trend, it actually inhibits that kind of phenomenon, right? We are not going today to go into the details of that. Just keep in mind that neurons can actually try to excite the others or inhibit the others, all right? We are in a freshman course, so we are not going to have big mathematical machinery to attack all the problems that are involved here. Neuroscience is a system science. It's been working and expanding over the last 50 years, and particularly the last 20 years very rapidly. But we have some tools here, right? Today we'll use our tools from Boolean mathematics to say some relevant things about the potential computations that can be done by nervous systems. We'll stop sometime at this level, talking about large-scale dynamics in brains and why criticality may be a relevant part of the story, and use mathematical methods we have seen in analysis of epidemic spreading. And we'll say something about single-cell dynamics, all right? So today we want to just go into kind of the first step that was successfully done in terms of trying to understand neurons as mathematical objects, right? To make a kind of a very brief reminder, a neuron can be seen as a system. Let me write down. This is not the only shape. You can have many shapes. Neurons are quite extraordinary kind of cells, right? You have seen cells that are more spherical, more kind of blobby in several ways, but this is a cell that has been developing and in such a way that you form these so-called dendrites, these very long-term, very complex, deformed extensions. So it looks like a tree, right? It can have thousands of connections with other neurons, right? This is the axon where you have the propagation of the impulse, right? This is the cell body. And what you will see is that this will be our input part. Other neurons, right, send signals to locations in the dendrites, right? And this is the overall activity, the overall excitation that is integrated here, right? What essentially makes the decision whether or not am I going to send signals to other neurons, right? Not only to one, to many of them, right? One thing for you to think about, right? We have already about 25,000 genes, right? If you look at the numbers, that for you as an exercise, you have about this quantity of neurons, all right? What is this telling us about the lack of information at the genetic level that is here? You know, to organize the brain, you need to organize a huge amount of neurons, right? With much more information than can be compacted within the genome, right? What is this telling us about the role played by other processes that are not genetic information? All right, so this is it's a rather complex and in itself fascinating system. But of course, if you want to make a model at any of these scales, right, particularly at the large scales, sophisticated models might be a problem, and we know that, right? And remember, again, I repeat that. When I'm drawing this, I might seem like a standard biologist saying something very well connected with reality, but this is a model too. I'm modeling all the time. So the big step in the direction that was made that somehow initiates mathematical neurobiology was made by two scholars, Warren McCulloch and Walter Pitts. McCulloch was a well-known physiologist, very reputed, one of the fathers of cybernetics. It was the 50s, right? And Walter Pitts was a child prodigy. He came from a poor family, and you can say that was largely uneducated. He actually left home as a teenager and showed up in the MIT campus at some point to attend the classes. He was essentially homeless, and immediately drew the attention of some of the scholars there, including mathematician Rudolf Carnap or Norbert Wiener, the father of cybernetics. No? So it happened that McCulloch and Pitts eventually get together and work in this outstanding paper, a groundbreaking paper, where they define the mathematical basis of neurobiology when Pitts was 17, right? Okay, what McCulloch and Pitts did was, we have a mathematical logic, a Boolean logic. They were familiar with different aspects of the problem, and they ended up in formulating a model that essentially translates this kind of picture with all the details we know into something much more simple, but that captures the logic of neuron dynamics. So the model assumes a number of things, right? Imagine I have a number of objects, I'm going to call it neurons, whose states are going to be in the set of zeros and ones, right? What is the meaning of that? Zero means that the neuron is not firing, it's in the rest state, whereas you have 1 if the neuron is firing, right? No activity, activity, right? Again, we know that the things are more complicated to some extent, right? Only to some extent. When you think in the axon and your propagation of the nerve impulse, you will study in lectures in other courses of systems neurophysiology, we know that the nerve impulse involves a potential change, right, in time. And this can have structure, right? And so it means that some analog computation is there, right? Nevertheless, the digital for us is going to be the relevant part, right? Whether I'm excited or not. So neuron states will be discrete, 0 and 1. Now imagine that I have all these neurons sending inputs to another neuron. Let's call it SI. Okay? In which way? Well, they are sending impulses, right, with some weights, right? We are not stopping here about what controls the weights here. Let's just mention briefly that the synaptic connection can be weighted, right? Because of the repeated activity, right? The way the neuron, the postsynaptic neuron is going to respond can be much more excitable, for example, more easy to excite, provided that experience has been there, right? So just have in mind that memory effects are going to be in the connections, okay? So I have my neuron receiving all these inputs, and these inputs will be weighted, right? Like here I have zeros and ones, but the way these zeros and ones will affect me depends on a wiring, right? Wiring is what here? Wiring is not an integer, right? Wiring is a real number. Okay? It could be continuum, it can be 0 because there's no connection, or can be negative or positive, right? For us, negative will mean that I'm trying to inhibit you, right? To suppress your activity or your firing, and positive is I'm trying to excite you. So the neuron is going to integrate, right? I'm putting the sum here indicating that I will gather all the information coming from my neighbors, right? My neurons that are acting as inputs, right? So that will be the set of things happening here, right? And here will be the outputs. And there's an additional quantity that is added here, which is called the bias. The bias is a parameter, it's a threshold parameter that says how easy for this neuron to react to the inputs, right? That's an important thing also to have. Not crucial, but it's important. Then, what happened with that? The thing is that I have this sum of things. The sum can be very large, actually. But my response, my final response to that, my output, has to be between 0 and 1, right? So to make sense of the formalism. So McCulloch-Pitt's model assumes that there's a process here, okay, that has to do with going through a threshold function, phi, right? That will take into account, if you want, this here, if you want to put the threshold here. A function that tells me whether or not excitation is enough to actually trigger a response, okay? All right, so how McCulloch-Pitt actually define that? What is this function? Very easy, and you'll find in the literature there's a number of variations on the theme, but the simplest case is the state of the neuron, this neuron at times t plus 1, again time in here is discretized, right? You might think that this is a limitation because discrete time sounds like a kind of toy picture of reality. But in fact, you can redefine the models we are going to discuss here in other lectures in a continuum, right? And in the continuum, you see the equivalent phenomena that we observe here, right? The good advantage of this is that with the tools we have, we can actually do the maths. McCulloch and Pitts say, all right, my response will be a threshold function, okay, that will involve what is the overall input acting on me by all the neurons involved in my system, right? And you see that I weighted. If this is 0, the neuron is not firing, it's not contributing. If it is, if it's 1, right, it will depend on the sign of the connection, what's going to be the nature of the actual input, all right, minus this threshold value, right? This is McCulloch-Pitts model. All right. So what can we do with that? Well, the first thing is that this is actually the basis of the vast majority of models that we use in neural network modeling, right? From the simplest models we can define, as some examples we'll make right now, to the really complex models that people is using in artificial intelligence. All right, so what else? What can be said? This is a representation of a formal neuron. But can this help us say something really important about what can brains do, right? It doesn't seem the case, but wait a moment. What McCulloch and Pitts did, among other things, was the following. Can we implement logic gates by using these kind of threshold functions, right? And how far can we go from that? I'm not following the scheme of McCulloch-Pitts model, which was published in the Bulletin of Mathematical Biophysics in 1952, if I'm not wrong. But instead, let's illustrate by example, right? How will you make a logic gate? Okay, let's take the simplest case. First, let's consider, for example, an OR gate. Remember OR gates, easy. We had essentially, for one input, let's say S1, S2, one input, another input, you have a function from 2 to 1, right? And this Boolean table is easy to define in terms of just writing down every single case, right? It's an OR function, so if one of the inputs is 1, the output is 1, okay? So can I do that using this formalism? Yes, in a very easy way. Assume that I have, now I'm going to consider that my formal neuron, right? I go from this general case to this simple case. 2 inputs, 1 output, right? Okay. I have a bias. This will be my neuron 3 if you want. These 2 have inputs weighted by some numbers. You will see that some arbitrary decisions here. And the thing is that S3 will be what? Well, in general, for a 2-input system, is the threshold function defined here, right? But it's much more easy here because I just have omega 1 S1, omega 2 S2 minus S3. That's all. That's the formal neuron for this particular case. If I want an OR gate, what I need is that if I'm trying to send, for example, activations, right? I want that at least if enough activation from one neuron is there, I want my neuron, my output to be 1, to activate, right? If both are working well, that will be the same, and only one case is excluded. If both are inactivated, I want my neuron to not activate, okay? Easy to do. Let's choose, for example, both inputs, are activators, right? Which makes sense. I will have that S3 will be simply S1 plus S2. And I have to decide now what kind of threshold I need to put there in such a way that if both are 0, this is negative, okay, right? This is negative, and the system gives a 0, right? I forgot to make a graphic that is necessary here, but you'll see I said it in words, right? The thing is, if this is not enough to overcome the threshold, right, this gives a 0. So here I put this quantity. Oops, sorry. This sometimes is called the field, right? HOI, because it's the amount, the total amount of input pattern that goes into my neuron. This could be the bias, right? So now I'm defining properly this. Below the bias, right? If the excitation that comes into the system is below the bias of the neuron, right? This gives 0. If it goes beyond this threshold, gives a 1. This is an excited neuron. This is resting. All right? This properly defines McCulloch-Gempitz model. So for my system, I just want this to happen in such a way that if the threshold is properly chosen, if both are 0, this is negative, I'm not activating, I'm in 0 state. If this is larger than the threshold, at least one of them is enough to be larger than the threshold, I get excited. It's not difficult to see that if I put a 1/2 here, I have it, right? If both are 0, it would be minus 1/2. I mean, if I'm in the domain below threshold, right, which would be 1/2, okay, I will not get excited, all right? Otherwise, I will get excited. Just if 1 is 1, is 1 minus 1/2 is 1/2, okay? So that could be an OR function, OR gate, right? How will you do an AND gate, right? It's easy. Let's just say very quickly. An AND gate, that could be a neural AND, OR. How you do an AND gate? Well, easy. You follow the same logic. Imagine I choose again this excitation for both input neurons, right? So omegas are 1. I need a new threshold that now has to act in the following way. Remember that an AND function is such that only one case goes through. It's 1, 1. 1, 1 provides a 1 as an output, okay? So what I need here, something that is, if S1 or S2 are 1s, is not going to be enough. But if both S1 and S2 are 1s, right, the overall amount here is going to be positive, and I'm going to have a 1. So I'm going to fire, right? If you put, for example, 3/2, you have it, right? 3/2, of course, is a number that is 1 among infinite. It's just a number I can use that fulfills that condition. For 0, 0, 0, 1, 1, 0, this is not enough. It's going to give a negative number. So 0, inactivation. If I have 1, 1, 2 minus 3/2 is larger than 0. So this implements my AND gate. This is the equivalent of a neural AND gate, all right? So what about a NOT gate? A NOT gate is peculiar, isn't it? Because a NOT gate is a NOT that actually inverts the logic. So what happens here is that, oops, if I enter a 0, I get a 1 as an output, all right? If I have an input that is excitation, the outcome is inhibition, is non-excitation, right? So how can I do it? You can see easily that it is actually a logic that tries to invert the properties, right? One way of doing that is by trying to inhibit the dynamics of the system. And it's easy to show that in this case, the logic and the implementation of this expression is limited to one input, right? So I don't need any of this, right? And so if I do that in terms of a neuron sending a signal to my other neuron, right, which has a threshold, here it's very easy to see what happens, and I only have one weight, right? So my neuron 2 will react in which way? Omega 1 is 1 minus the threshold, right? Well, I want to do the opposite of the entrance. So the way of doing that is using a negative connection, right? And actually, you can do that by making the opposites of everything here, right? Let me put it here. If omega 1 is minus 1, right, I will have minus S1 of t. And now I need to put a threshold, right? In what way? In the way that if this is a 1, when I make the overall sum here, I have something that is 0. So it's negative, sorry. It's negative, so the input is 0. So a 1 gives a 0. One way of doing that is actually by choosing a threshold that is, instead of positive, is negative, right? If it's negative, remember that this is a minus sign here, right? I put it here. And you see this, it works. It's a threshold condition where if this is 0, right, the entrance is 0, this is positive, so the output is 1, okay? If this is 1, you have an overall value minus 1/2, negative, output 0, all right? Now, what else can we say beyond the classification, right? One of the things that is really, really important here is you can implement NOR gates or NAND gates that, remember, are especially important gates. For example, what about a NAND gate? Remember that, let's make it like this. Remember that a NAND gate is a gate that inverts the AND gate. So if I write down all the possible inputs here, all the pairs, an AND gate will be 0, 0, 0, 1, because it's only favorable case. The NAND gate is right the opposite. Okay? How can we implement that? Well, you see here the philosophy. If you want to do the opposite of a standard gate, you just need to use negative connections, right? In this case, my neuron following again this scheme, okay? 2 input neurons, 1 output neuron, right? Could be McCulloch-Pitts, 2 inputs, all right? And weighted, and then my threshold, right? How about doing this? Imagine that I use negative values, right? For omega 1, omega 2, take it minus 1. Again, I could use minus 0.9, right? It would be exactly the same. I just need to rescale. I will have minus S1, minus S2, and I need a threshold, right? How do I want this to work? Well, I want that table to be my output, okay? So what threshold I need to choose. So if I take, for example, 3/2, what's going to happen? If I use 3/2, if these two are 0, okay, I'm going to have something that is positive. When I say 3/2, sorry, I'm saying the total sign here, so which means if I use a threshold of minus 3/2, which will give 3/2. So let's see that this is consistent. Using 3/2 as a threshold, or minus 3/2, right? You see that if both inputs are positive, 1 and 1, right? That would be minus 2. Minus 2 gives a negative number here, so the output is 0, right? Instead, if any of them is 1 or 0, so let's see, if 1 is, for example, I have 1, 0, I will have a minus 1, not enough to change the sign of 3/2, so this is positive, and the output is 1. The same happens with this number and this combination, right? So this effectively implements a neural NAND gate, right? And you could do the same. You could do the same with the NOR gate, right? Why I'm referring to NOR gate or NAND gate here? Well, for a reason that we already discussed at some point. Because only with NAND gates, only with NOR gates, you can actually build any Boolean computational device, right? That includes a computer. And that's why McCulloch and Pitt's work has a really important consequence that we can actually see here with this formalization. The brain can do at least anything that a Boolean computer can do, right? So this simple formalism automatically allows us to respond to that question. So about a potential boundary, a potential bound for the computational capacity for a living brain, right? McCulloch's model, by using this kind of formalism, even with all the limitations that we have included in simplifying the picture, provides that lower bound. To the least, our brain can do what a computer can do. Now, the next step in the analysis of this very simple picture of neural systems is going to what we call usually neural networks, right? This is, of course, a piece of the cake, right? It's the single system neuron. The kind of diagrams we just show are kind of the simplest instances of where you can already start to say neural network. It's more appropriate to say neural gates, right? Again, feed-forward circuits. But what happens when we connect neurons between each other in such a way that we can actually have feedbacks into the system, right? That's what makes neurobiology so exciting. And that's actually what pervades the real complexity of neural systems. So, for example, consider the following case, right? Imagine I have a neuron, right, that is sending signals to other neurons. I'm going to use a very simplified picture of things. All right. Let's say here and here. Okay. Now, each neuron does whatever it does, but let's assume that this neuron also sends a signal to this one, so you have two inputs for that one. This sends also, this receives. These diagrams usually get complicated. Input for this one, input for this one, all right? So we make a circuit where essentially everyone receives inputs from the other two neurons, okay? So I have inputs here, all right? So that could be a simple, but already you can see a bit clumsy neural network, right? And my question is, what kind of phenomena can I observe coming out from these systems? All right? Okay, you can easily figure out that because we have made a mapping between logic gates and neural gates, everything we use in the context of gene networks can be applied here. And that's not some kind of strange phenomenon, which would actually see that neural networks and gene networks share a number of really important dynamical properties, right? In particular, this threshold-like behavior. So we can actually use circuits as the ones we have described previously, like NOR gates connected, as soon as I remember that this element here, for example, can be seen if this is neuron 1, neuron 2, and neuron 3, right? Can be seen as a circuit where the two neighbors send my signals, the signals that are weighted and integrated, all right, by my neuron 1, right? The equivalences are the same, so we can actually say if the weights are this and this, once I know they are logic gate, the mathematics are exactly the same, equivalent, right? So it's easy to build exercises with that. The only thing that we will need to do is to know what weights are there, right? So I will have weights like this one here, right, affecting this neuron, etc., etc. I think it's more interesting to look at one of the interesting phenomena that emerge here, which is what we call attractors, right? Attractors that we already seen in genetic networks here will play a especially interesting role. Take as an example, because it's easy to do, right, and easy to implement, the majority problem, right? The majority problem, sometimes called the majority rule, says that the dynamics of my system, in this case, I'll say S of any of them, any of these neurons, right? If the state, again, is a Boolean number, will be called the majority of S1, S2, S3, right? It's a threshold function in some way, because what we're saying is this rule says that the output is going to be 1 if I have majority of ones, as simple as that, on 0 otherwise. Or in other words, saying that 0 if the majority are zeros, right? Since there are 3 numbers, because I include myself there, right? It's easy to actually define the function. How this will read in terms of McCulloch-Pitts formalism, right? Well, any of the neurons, because they are detecting all the states, including themselves, right, will have the same response function. That makes this especially simple in this case. Because what they actually do is to know what is the state of the overall system. In other words, in this case, 3 states. I just need to know, because there's no weights here, I just need to know how many are zeros or ones. So I just need to compute the total amount of activity, if you want, in the system, and then use the right threshold to decide if this is larger than 0 or less than 0 or larger than a given value. In particular, it's easy to place this because you see what numbers I can see. Well, I can have everyone 0. I can have just one element having 1, 2, 3. That's all the states possible in my system, right? If I am below this threshold, right, it means that I either have this or this or this, or this, right? This is the majority of numbers is zeros. If I'm here, right, it is because I have two ones, or because everyone is a one. So where is the threshold? What decides whether the majority is 0 or 1? Well, I take a number here, 3/2, for example, but any number here will work, okay? That's arbitrary. If I use that, this particular instance of McCulloch-Pitts rule, right, gives us the majority, okay? This will be 1 if the majorities are 1, if 0 if the majority is 0. Okay, how this looks like when I use the Boolean cube, right? Well, in a moment you will see that this is telling us something really interesting. As usual, this 0, 0, 0, 1, 1, 1. Okay? All right. How it looks like? You can make the table if you want, right? I mean, the Boolean table with all the potential states, and since every single element goes into the same next value because they are all affected by the same function, it's very easy to do. And what you will find out is you have a number of states that go into the 0, 0, 0. Which ones? Well, those where the majority is of zeros, all right? All those go into the 0, 0, 0. That's one attractor. And all the others go into this other state, right? Which ones? Well, were those that have a majority of ones, all right? Okay, so two attractors in the dynamics. I either go here or here. And then two basins of attraction, all right? I go, all of these go into this state. We call it the basin of attraction for this state, right? Or all these states go into this one. That would be the basin of attraction of 0, 0, 0. Why is this important? Well, let's make some connections and advance some really relevant ideas. On the one hand, this is a problem that is connected with something we have already seen before, right? The problem of symmetry breaking. You have a completely symmetric system with two potential attractors that are stable states, right? And then a neighborhood, okay, that flows into that attractor, provided that you start from the right place. Remember that in symmetry breaking, we had two alternative states. Everything was completely symmetric, and provided where you started from the landscape, right? If you want, this is one attractor, the other attractor, and that was unstable. We go into one basin or the other. That's a discrete analog of what symmetry breaking is, right? In a very low dimensional space, we haven't yet put the attention onto that, but in a realistic neural network, right, we live and we work in a multi-dimensional space, right? Highly dimensional space, in fact. All right, that's one thing. The other thing is that in the context of neural networks, as you will discover at some point, this is profoundly connected with memory. With memory, and one kind of memory that is special to us as living beings, right? It's called associative memory. What is associative memory? Well, let me give you an example. We look every day at objects around us that are just representations of reality, right? When we look at a picture of a person, we know that who are we looking at. despite that this is a two-dimensional picture, right? But can be from someone from a while ago, so it's not exactly like now. It's much smaller. And we actually can go beyond that, right? If, for example, I use a cartoon of someone, all right? For example, if I do this, at least for those of you who like the movies, this is not the real person, right? This is a caricature of one of the Marx brothers, right? So not the real one at all, not a picture. But we have no problem. You have seen it before. We have no problem. And actually, if I just draw something like this, it's very likely that someone says, "Oh yes, Groucho Marx," right? And if some time in the future you go to a friend of a house, the house of a friend, sorry, and you see on the table something like this, it's a piece of paper covering that, you might be pretty much able to say, "Oh, is this Groucho Marx?" Right? Associative memory means that we have learned from the past about a number of objects, okay, and we have stored that information. But this information is enormously reliable and easy to recover. In other words, incomplete information about something we have learned can be recovered automatically by our brain, right? Important messages. One, there's no program, there's no computer program with a standard algorithm that allows for associative memory to work, to happen, right? It's no such a thing. It's something that a biological system or the analog that we do when you do these models can do, okay? And that connects with other very important problems, right? When I say that associative memory works this well, I'm meaning that in our neural network, which can actually have many minima, right? Every minimum of this network is a memory. And if you are here, it means that, for example, you remember Groucho, right? You know that the object you're seeing belongs to that class, right? But if you're here, you might be in this case of incomplete information. Something is missing, and maybe a big chunk of the whole thing is missing. But nevertheless, you actually are able to reconstruct, because the network has a dynamical pattern of work, to reconstruct the whole information. That's connected with a huge amount of really interesting problems with disease states. What happens when I have a network and I damage connections, right? And among other things, what happens is that you'll see that the system is able to keep going without almost no problem, which is something that is consistent with the idea that we lose neurons every single day. And nevertheless, we keep working pretty well. But also there are thresholds. Thresholds, some of them connected to the problem of percolation that you have heard about. When you destroy enough connections, the system becomes a non-system, right? Becomes disconnected. And that may be pretty much the case behind some of the diseases of brain dynamics that are called disconnection diseases. Diseases that are connected to the fact that by destroying the wiring, you cross thresholds, and the thresholds are what we call diseases.